Okay, so let's now proceed to the problems from section 8.2. And these are all problems that can be solved by the technique of integration by parts. So this is integration by parts. This is section 8.2. Now what you probably remember from integration by parts is the formula integral of u dv equals uv minus integral of, v du. Now, I want to point out to you that this formula is really shorthand for the following expression because, see, the u and the v, where do those come from? Because when you actually look at formulas, you see x's and t's and things. You don't see a u and a v. So what this means, so say the variable of integration, say it's x, then what this really means is the following. It means integral of u of x times dv dx dx is equal to u of x v of x minus the integral of v of x du dx dx. See, because this is all an expression in terms of x. And of course, if the variable of integration was t, then I would just be putting in t for all the places where the x is. So this is what this really means. This formula here is just shorthand for. So this is shorthand for that. This expression here. So in this case, the name of the game is choosing two things. You have to choose what part of the integral is going to be the u, and then what part is going to be the dv. I guess in that sense, you're only choosing one thing really, because whatever you choose as your u, whatever is left had better be your dv, or else you're out of luck. So let's proceed now to work the first problem there. So let me copy it down here. This is problem 12, integral 5x over e to the 2x dx. Now a thing that's convenient to do first is to rewrite this as a product. 5x e to the negative 2x dx. Why? Well, because in your formula u dv equals uv minus integral of v du. You don't have a quotient of anything. You have a product. You have a u times a dv. So I want to have a product in the integral. And you may remember actually from Calculus 2 that integration by parts can be viewed as an inversion of the product formula for differentiation. And that will be explained in your calculus book somewhere. I'm not going to rework it right now, but you can look it up wherever it is in there. So we want to write it this way first as a product. And then once we do that, a good choice for u, so this will be u equals 5x. Then if we make that choice, du will be 5 dx. Then dv has to be whatever's left. It's e to the minus 2x dx. And then this will tell you that v is minus 1/2 e to the minus 2x. Now, to go from dv to v, I'm really integrating something. You know, I'm taking this thing and I'm integrating it. I'm taking integral of minus e to the minus 2x dx. And if you forget, whether it should be a minus sign or a plus sign, or if it should be a 2 or 1/2 here multiplying this, you can just differentiate it again. I mean, if you take the v here, then if this is v, then that would say dv dx equals, well, the 1/2 comes out, and then I have e to the minus 2x. And then the chain rule says I take the derivative of what's inside, which is minus 2. I forgot my minus here. The minus 2 cancels with the minus 1/2, and I get e to the minus 2x. And so I'm thinking of this expression, dv dx equals e to the minus 2x, as something where I can multiply both sides by dx. The dx's cancel, and I'm left with my dv equals e to the minus 2x dx, which is the original choice I made. So I know this is the correct integral of that dv. But this is all just commentary. Once I've made those selections, I can take the integral and rewrite it now as uv. So this is going to be 5x. And then v is minus 1/2 e to the minus 2x. And so that's my u, my v. And then minus the integral of v du. So the v, once again, is minus 1/2 e to the minus 2x. And then du is just 5 dx. That's coming from here. Okay, so then I can proceed to write this as minus 5 over 2x e to the minus 2x. The minus and minus will give me a plus. The 1/2 and the 5 will combine to give me a 5 over 2. So I have a 5 over 2, and then what's left is just the integral of e to the minus 2x dx. And that's the one that I just did. You know, we're talking about integrating this. And so this will come out to minus 5 over 2 x e to the minus 2x. Well, there's going to be a plus 5 over 2, and then what's going to be inside here is a minus 1/2 e to the minus 2x, and then there's going to be a constant of integration. And so then finally we can simplify this one more time. Minus 5 over 2x e to the minus 2x. This is going to give me a minus 5 over 4 e to the minus 2x plus c, and that's the answer. So that one wasn't too bad. You want to choose your u to be something that will simplify when you differentiate it, and you want to choose your v to be something that is possible to integrate. And so we'll repeat that reasoning again as we look at some of the other problems. Okay, let's move on to number 24 here. This one looks a little scary at first sight, I guess. Integral of t cosecant t cotangent t dt. Now, how do I motivate, how do I explain to you why I make the choice I'm going to make? In order to do this, you would have to kind of remember that the derivative with respect to t of cosecant t is minus cosecant t cotangent t. Because then you can sort of recognize that this part here ought to be the dv. Because if what I have is the derivative of something, then I know how to integrate it. I guess you could get lucky though, because you could say, well, I want my u to be t, and then my dv has to be whatever's left. The reason I would want my u to be t is simply because it simplifies when I differentiate it. In any case, a good choice to make will turn out to be let u equals t, and then du will be dt, and then dv has to be whatever's left, so it had better be cosecant t cotangent t dt. And then that will tell you that v is negative cosecant t. And once again, you could tell by differentiating this that it's this here. By the way, if you forgot what the derivative of cosecant is, that's something that once again is easy. In a minute you can figure it out. If I have so d dt cosecant t, this is d dt 1 over sine t by definition, and then I have the quotient rule, low d high, so this is sine t is the low part, d high that's derivative of 1, which is just 0, minus high, which is 1, d low, that's just cosine t there, over the bottom squared, so this is sine squared t. This part goes away, that's just 0. The minus 1 folds into that, so this just gives me minus cosine t over sine squared t. And then I can break this into equals minus 1 over sine t cosine t over sine t. Well, so that's just minus. The 1 over sine is by definition cosecant t. The cosine over sine is by definition cotangent t. So, notice here, I took the derivative of positive cosecant, so I got negative cosecant cotangent. Here, if I take the derivative of negative cosecant, I'm getting positive cosecant cotangent. In any case, this is something you could work out really fast if you needed to, if you forgot what it was. So you're not helpless in that context if you can't just remember the formula. Okay, so suppose that we've made these choices. Then the integral will be, I'm going to have my uv, so this is going to be a t, times the v was minus cosecant t. So this is my uv. Then I'm going to have minus the integral of, well, v is minus cosecant t. du is just dt. And so what I have so far is minus t cosecant t. Let me first point out to you that this was minus integral of v du. That's the whole point. But I'm going to take out this little bit of commentary here because I don't need it there. So this I'm just going to write as minus t cosecant t minus a minus. So this will be plus integral of cosecant t dt. Now it turns out that this integral, in a sense, it's fair game to just remember what this integral is or look it up, because this is one of the elementary trig functions, or at least it's 1 over one of the elementary trig functions. So it would be acceptable on your homework here to just look up what it is, and it would come out to be negative ln of cosecant t plus cotangent t plus c, and that would be the answer. But just so you don't think that I'm cheating by not telling you how to solve this integral, I will tell you how to solve this integral. It involves a trick. So there's a trick. And what you do is so if I want to integrate cosecant t dt, what I do is I first write this as cosecant t, and then I multiply and divide by something, namely cosecant t plus cotangent t over cosecant t plus cotangent t dt. So I haven't changed anything. I've multiplied by something, I've divided by the same thing, so this is still valid. And then I can write this as integral of, well, I'm going to take the denominator there, and so I'm going to write 1 over that thing, cosecant t plus cotangent t. And then I'm going to take this and multiply it through here and get myself a numerator of cosecant squared t plus cotangent, or cosecant rather, cosecant t cotangent t dt. Now I'm going to make a u substitution, or I'm going to say let u equal what's in the denominator here. So this is cosecant t plus cotangent t. And then if that's true, then du, then I differentiate these things. I'm going to get a du is minus cosecant t cotangent t. That's coming from this term here. And then from this term, I'm going to get a minus cosecant squared t. And all that is times dt. Now if you look at it, this thing here, this whole part here, is minus what's in here besides the part over here. So this whole thing collapses to, and I don't really have room to write it, so I'll just write it up here. This whole thing collapses to nothing but minus integral of 1 over u du, which of course is minus ln absolute value of u plus c, which is minus ln, and I said what u was, it was cosecant t plus cotangent t inside the absolute value plus c. And that's exactly what I wrote here. So that's why it's true, but you probably don't care about all those details.